Hello, good evening everyone. I am Ryan Kim Nuevo and tonight we will discuss the topic about wind as a gradational agent. What is the wind as a gradational agent? Wind as a gradational agent refers to its role in shaping the Earth's landscape through erosion, transportation, and deposition of materials. Winds are an active agent of degradation mainly in the desert because of lack of vegetation or poor of vegetation. While wind is generally considered less effective compared to other agents like running water, waves, groundwater, moving ice, and mass movement, it can still significantly contribute to the landform development under certain conditions. Landforms created by wind-driven processes are known as Julian landforms, derived from the name of Julius, the god of the winds in classical mythology. As a continuous process, wind is involved in erosion, transportation, and deposition of materials, contributing to the formation of various landforms and landscapes. Let's go and watch some video clip for you to understand more about wind as a gradational agent.
Agents of gradation. Wind. Wind is an invisible form of air moving from a region of high pressure to a region of low pressure and is also the third agent of gradation. The action of wind as an agent of gradation is most widespread in places like deserts because of the dryness and lack of vegetation in these places.
Now let's move on to the erosion by wind. Wind erosion occurs predominantly in arid and semi-arid regions where loose surface materials are readily available. Strong winds whip up these materials and transports them within turbulent air currents. The process of erosion by wind involves the two primary mechanisms, the deflation and abrasion. First is the deflation. Similar to the hydraulic force of running water, deflation refers to the removal of fine particles such as clay and silt from the surface. As wind velocity increases, the fine particles at the surface, often microscopic bits of dust, are lifted into the air and curled in suspension. These particles will remain suspended as long as the upward air currents exceed their tendency to fall to the ground. This process is particularly effective in regions with minimal vegetation cover, as the absence of plant roots allows wind to easily dislodge and transport these materials. Next is the abrasion. Abrasion is the process by which wind-borne particles, such as sand, impact and wear away the surface of rocks and other materials. As the wind transports sand grains and other particles, they collide with exposed surfaces, gradually wearing them down over time. This process is similar to sandpaper rubbing against the surface, causing it to become smoother and polished.
Hey guys, welcome back to A-Level Lessons. In this video, we're going to be looking at our next part of physical geography, covering erosion by wind. So we're going to be looking very specifically at two erosion processes that basically occur when wind is present. Alright, so this will be highly applicable to your areas such as aeolian processes, your aeolian environment, aeolian landforms, anything that's got to do with wind. These erosion processes would tend to play a role. Alright, there are two main types of erosion processes by wind. So firstly, you have deflation, and the next one will be abrasion. So as you can see from this diagram, we can actually see that there is abrasion happening over here, and we'll discuss more about what exactly this process is, right? If you look at this diagram, it is basically wind transportation processes that are basically happening over here, right? Sortation, creep, attrition, and suspension. So there's another video that I did on everything about aeolian processes. You can go and check it out. I'll leave a link in the top right hand corner of the screen. Go check out that one if you want to know more about aeolian deposition, aeolian transportation as well. So firstly, we have deflation. So deflation refers to the picking up of dust or sand and loose rock fragments. So it is very simply the picking up. So think of it as though you're using your hand, you're just picking up a piece of sediment. That is basically what deflation is. So it is also the entrainment of loosened materials by wind over time, which causes the ground to be lowered. Alright, so what this actually means is that the wind basically lifts these particles up and removes these particles from the surface. So think of it as though it is filtering out these particles. Right, it operates on a localized scale, as it takes a very long time for all of these small sediments to actually travel a long distance. So deflation can literally be just the picking up of dust in a localized area, and then maybe it travels via wind transportation a few centimeters, a few meters, and then it is basically dropped out again, right? It's deposited. So deflation itself is an erosion process, as it essentially erodes the ground by picking up these sediments. So think of the ground as originally being filled with a lot of tiny sediments, but one of them, use the blue pen, one of them has been taken out. So as a result of it being taken out, erosion has taken place, right? Erosion is essentially anything that, think of it as any sediments or any part of a ground that is being chipped off. Alright, so finer materials such as clay, silt will basically be the ones that have to go through weathering first, right? So they're often pre-weathered by salt weathering. Apologies. So they're often pre-weathered by salt weathering, which is a physical weathering process. I've covered that before as well. Go and check out that video before going through deflation. Alright, so essentially these materials, they have to be broken down a bit more first before they can be entrained and picked up by the wind. So erosion is shown as particles are eroded, like I've mentioned just now, as well as when the ground is lowered. So in certain cases, like we just discussed, when you have a lot of particles that are basically made up on the ground, right? If the whole of this top layer has been deflated, right? They've been picked up and brought over somewhere else. You notice now the ground surface will become lower. Originally, it was up here. It is now at number 2. It has actually been lowered, right? So that is when you can see that erosion has taken place, right? So until the water table is reached, it's a bit more of a exaggeration, right? It's usually going to happen rather slowly, this process of deflation. Moving on, we have abrasion. So abrasion, similar to that which you have learned in your rivers, right? The abrasion that occurs in rivers is essentially the mechanical wear of rock or sediments by the impact of particles in saltation. So saltation is a process whereby essentially your sediments, think of them as skipping, right? They are skipping on the ground, right? So you have the ground, your sediments are skipping. So when your sediments actually skip, they will hit the surface, and that causes abrasion to occur, right? It causes wearing of sediments or rock that is on the ground, right? So the bouncing particles would constantly or commonly dislodge other grains when they strike the surface, and so the number of particles would diminish with height, right? Naturally, as the particles skip and they dislodge more and more sediments. So the repeated collision of sediments would cause abrasive friction to take place, hence resulting in deformed sediments and rocks. Alright, so as your sediments continue to collide with one another, it will basically cause friction and a lot of dislodging of sediments, which causes your rocks to become very odd in shape, right? They become a bit deformed, right, as sediments are being chipped out of it.
And now, let us know the factors influencing wind's effectiveness. The efficiency of wind as a gradational agent is influenced by 2 primary factors: the absence of complete vegetation cover and the presence of dry, fine materials at the surface. In regions where vegetation cover is sparse or absent, wind is less impeded, and its velocity near the surface is higher. Conversely, continuous vegetation cover reduces wind velocity, absorbs its force, and prevents direct impact on the land surface. Additionally, plant root networks help hold materials in place, acting as a protective barrier against wind erosion. Arid regions and beaches are examples of environment where such limited vegetation cover is common, allowing wind to play a significant role in shaping the land. The second crucial factor is the presence of dry and fine-grained materials at the surface. Under such conditions, strong gusts of wind can easily detach and remove particles, leading to erosion and transportation. However, damp particles tend to adhere together in wind-resistant aggregates, reducing the erosive potential of wind. As a result, regions with dry fine materials exposed at the surface, such as dry riverbeds, areas of recent alluvial or glacial deposition, newly plowed fields, and overgrazed lands, are also prone to wind-driven erosion and landform development. And now let us move on to the formation of Julian landforms. Julian landforms are the products of wind-driven processes on the Earth's surface. These landforms vary depending on the characteristics of the landscapes and prevailing wind patterns. Some prominent Julian landforms include sand dunes. Sand dunes are formed by wind-driven sand accumulation. Dunes are common in desert regions and coastal areas. They take various shapes such as crescent, linear, and star based on wind direction and sand availability. Sand dunes are classified into several types based on their shapes, sizes, and characteristics. The major types of sand dunes are as follows. First is the Barcan dunes or the crescent dunes. Barcan dunes are the most common type of sand dunes. They have a crescent or U-shaped form with the tips of crescent pointing downwind. These dunes have a gentle windward slopes and steeper leeward slopes. Barcan dunes are typically found in areas with limited sand supply and consistent wind direction. Next is the parabolic dunes. Parabolic dunes are similar to Barcan dunes, but their tips point upwind. They formed due to vegetation stabilizing the sand on the leeward side, preventing further migration in that direction. And the next one is transverse dunes. Transverse dunes are long ridge-like dunes that form perpendicular to the prevailing wind direction. They have straight or slightly sinuous crests and are often found in areas with abundant sand supply and consistent unidirectional winds. Next is the longitudinal dunes. Longitudinal dunes are elongated and parallel to the prevailing wind direction, similar to linear dunes. However, they have more irregular shapes and crests. Their unique characteristics and formation make them valuable elements of deserts, ecosystems, and intriguing subjects for scientific study. And lastly is the blowout dunes, also known as blowout depressions or simply blowouts, are a specific type of sand dune formed through wind-driven erosion. Unlike the typical sand dunes that results from sand accumulation, blowout dunes are created by the removal of sand from the surface. They are characterized by their bowl shape or saucer-like depressions, which form in areas where loose sand is exposed and susceptible to erosion.
In order to understand how a sand dune forms, we need to understand how sand moves. The way one sand grain moves is how they all move, and together they make a dune. So let's see all the ways that one particle of sand can move from point A to point B. There is suspension, saltation, and surface creep. Suspension is what happens when the sand particles get suspended in midair. Strong winds are able to pick up the smallest of sand grains and whisk them away. Larger particles are transported by saltation, that is, short distance jumps along a path. As saltating grains bounce around, they'll sometimes push out the largest sand grains and cause them to exhibit surface creep. This is when exposed sand is pushed or rolled along the ground. Of these three methods, saltation contributes the most sand for dune formation. And so the sand moves, starting as a patch only a few centimeters high in a spot where the wind loses a bit of speed. It grows to anywhere from about 4 inches to a little over a foot, peppered with wind ripples. Sand continues to accumulate, and when the proto-dune gets to about 10 to 15 inches, a visible slope forms with sand falling down one side. It keeps growing, and finally it hits about 3 to 6 feet, creating a proper Barken dune. That's the first dune name I've thrown at you, but naming dunes isn't easy, as there really isn't a universal standard for dune categorization. With animals and plants, colloquial names exist and vary from place to place and person to person, but at the end of the day, Latin names ground these labels in a level of specificity that dunes just do not have. And that's partly because we know so little about them. Most of what we do know was only discovered in the last century, and it's all still relatively new. What we do know is that different sand dunes are created in different ways, so in order to understand their formation, we need to understand their identification. Now, individual scientists will group and name dunes a bit differently and value their importance in varying degrees, but we've got to start somewhere, so let's return to the humble Barken dune, but this time from a top-down angle. Barkens have a distinct shark-toothish shape. If the wind is blowing in one direction, they can hold that shape for a long time and a long distance. You can see here 19 Barken dunes moving a third of a mile over the course of 40 years. Back to Barken dunes for a second. We can see that a bidirectional wind regime is not the only factor that can transform them into something else. How much sand that wind is carrying makes a big difference. In fact, more sand can turn multiple Barken dunes into a Barkenoid ridge, and then again into a transverse dune. Why are they called transverse dunes? It's because the wind direction is transverse or perpendicular to the crest of the dune. When either complex linear or complex transverse dunes, more on that label later, stumble into areas with even more complicated wind regimes, they can continue their evolution. The new wind regime can change the direction of the crest of this transverse dune, making it a reversing dune. Not really a dune type unto itself, but more of a subtype. It's just a label given to any dune that periodically reverses direction. Anyways, as the seasons change and winds come in from different directions, arms will grow out of the form and a star dune is created. And they're as spectacular as they are rare, but what they lack in frequency they make up for in size. Not only do they typically hold a greater volume of sand than any other dune type, they're also the tallest, sometimes reaching heights of more than 1,000 feet. The last of the major dune types carries with it a little something from all the others. Parabolic dunes are as aptly named as the star dune, as fond of a unidirectional wind regime as transverse and Barken dunes, and much like vegetated linear dunes, their creation is guided by the plant matter they form around.
Sand dunes made of millions of finely divided sand particles. I have a few million sand grains right here. Unfortunately, they've become mixed with pebbles and pieces of gravel and coarse sand as well. But some of it is beach sand. Can you suggest a way how I might separate the bits and pieces from this mixture? Well, if I have a sieve or some sort of straining device, maybe I could use that. I could pour the mixture into it and shake it around for a few seconds, and very soon the fine particles, the sand, fine and coarse sand, go through, and some of the small stones, the larger stones, stay behind. Now what if I want to separate this mixture? Well, I could use another sieve or strainer, this time a bit finer than the first one. And this time, only the fine pieces of sand will go through, the coarse sand stays behind. So that's one way of separating the bits and pieces of a mixture of sand and stone. But there are other ways of separating the same sort of mixture without doing anything at all. Let the wind do the work for you. Here's the same mixture once again, and I'll simply tip it out, and we'll wait for the wind to blow. You might say, he'll be waiting a long time. Ah, no, we happen to have a wind machine in the form of an electric fan right here. Now you watch the bits and pieces of the mixture as the wind starts to blow. Right? Immediately, some of the fine sand grains blow away. In fact, they're going off the edge of the table right now. I can see them in the millions going over the edge of the table. And if you look at the original mixture here, you notice that the larger stones, the pebbles, the pieces of gravel, are staying right where they are. Some of the smaller stones are actually starting to move, and they roll across the table, or they move a little bit away from the pile. But if we leave that fan long enough, and if we allow for other things moving the bits and pieces around, in real life, maybe water from rivers, water from the rain would spread the bits and pieces out, and then the sand would be blown away. In other words, the wind does all the work of separating the bits and pieces. And very soon, you'd have stones here Small stones and large sand grains there, and right off the edge of the table, the little fine sand grains, gone for metres down the track. And that's the sort of thing that happens in deserts all the time. If you look at some of the deserts in the centre of Australia, very often you see a lot of red sand and red stones, red pebbles. If you look more closely at those sand grains and the rocks, you find other interesting things as well. Here's an aerial shot of the Simpson Desert. Now you'll notice that there are lots of long grooves, some of them stretching for hundreds of kilometres. Those grooves have been formed over millions of years by the action of the wind, blowing sand away and forming long grooves. There's another very interesting desert in the centre of Australia called the Stony Desert. And if you look at the Stony Desert, you find just what the name tells you. Lots and lots of stones. In fact, it looks very much like the stones that we had right here in front of the fan. Those stones in the Stony Desert are called gibbers. It's called a gibber desert sometimes because gibber is the Aboriginal word for stones. Well, let's get rid of the Stony Desert and go back to the sand dunes. We can make some sand dunes very easily by turning the fan off and then putting some little heaps of sand on the table. There's one there. Make it a little bit higher. A couple of others, smaller one there, another one over here, perhaps one over there as well. And we'll set the wind going and you'll see on a small scale what happens in the real world when wind blows over loose, finely divided particles of sand. Watch those little heaps of sand and you may see some changes in shape. The wind is blowing, look at that. Already the sand is moving away. The wind is coming from this direction. Look what's happening. On the direction from which the wind is coming, it's gradually spreading out so that there's a more gradual slope. You see that on that one there? You may notice it on this one as well, and certainly that one there. The side away from the wind becomes more steep. And so each of those little heaps of sand forms a sand dune. It's very much the shape of a sand dune as you know it from visiting the beach. Gradual slope here, steeper slope down there. You may notice something else as well. They're actually creeping along. They're creeping along all the time, very slowly. Sand is rolling up here, down there, and some of it's leaving as well. And one of them's almost left the picture over there. And that's what happens all the time with real sand dunes. And they're very beautiful, whether they're at your coast or like these in Colorado, which form a magnificent park of sand dunes. Those are huge sand dunes, some of them hundreds of metres high, and the sand is moving all the time. Sand dunes themselves are beautiful things which move, but there are some plants that are clever enough to actually put down roots in those moving sand dunes and hold them up for a while and actually go through their life cycle right there in the dunes. Have a look at this.
And the next prominent Julian landforms is the Lewis deposits. Lewis deposits are accumulation of fine wind-blown particles, predominantly composed of silt-sized particles with some fine sand and clay. These deposits are usually loosely packed and have a characteristic yellowish or light brown color. Lewis forms when wind carries these fine particles over long distances and deposits them in specific regions. Lewis deposits are primarily formed in regions with a significant source of fine-grained materials, such as glacial till or alluvial sediments, and where the landscapes is relatively flat and exposed. During periods of arid or dry climate, the exposed fine particles become susceptible to wind action. Next is the yardangs. Yardangs are streamlined elongated ridges formed by wind erosion. These landforms typically occur in regions with parallel wind patterns and are found in areas with soft rock layers that erode more rapidly. The prevailing winds gradually wear down the surface, sculpting the landscape into elongated groove landforms. Yardangs are commonly found in arid and desert regions, and their shapes are determined by the dominant wind direction. And next is the desert pavements. Desert pavements are the result of wind erosion, removing fine-grained particles from the surface, leaving behind a layer of coarser fragments. These coarser fragments, such as pebbles and gravel, create a distinct surface covering that protects the underlying material from the further erosion. Desert pavements can be found in our regions where wind efficiently removes smaller particles, exposing the coarser material beneath. And lastly is the ventifacts. The ventifacts are rocks that have been shaped and polished by wind abrasion. Over time, the impact of wind-driven sand or silt particles wears down the exposed surfaces of rocks, resulting in a flat, facets, and grooves. The facets on ventifacts are aligned with the prevailing wind direction, serving as a valuable indicator of wind patterns in the past. Ventifacts are commonly found in deserts and other arid regions where wind erosion is prevalent. And now, let us know the specific locations where wind has played a significant role in shaping the land. First is the Namib Desert, Namibia. The Namib Desert is known for its vast sand dunes, some of which are among the world's tallest. The dunes are shaped by persistent winds blowing from the Atlantic Ocean, eroding sand from the coastline and depositing it further inland. Next is the Great Sand Dunes National Park in USA. It is located in Colorado. This national park features large sand dunes formed by wind-blown sand from surrounding mountains. The dunes' size and shape change over time due to wind patterns. And lastly is the Chinese Loess Plateau. The Loess Plateau in China is a significant area with thick loess deposits formed by wind-driven accumulation of fine particles from the Yellow River Valley. The Loess soil supports extensive agriculture in the region. So before we proceed to our mini quiz or knowledge check, let us recall first the topic. Wind as a gradational agent plays a crucial role in shaping the Earth's landscape through erosion, transportation, and deposition of materials. It is particularly active in arid and semi-arid regions where lack of vegetation allows it to effectively dislodge and transport fine materials from the surface. Wind erosion involves two main mechanisms, and that is deflation, which removes fine particles from the surface and transport them in suspension, and abrasion, where wind-borne particles impact and wear away exposed surfaces. The effectiveness of wind as a gradational agent depends on two primary factors: the absence of complete vegetation cover and the presence of dry fine-grained materials at the surface. Regions with limited vegetation and exposed dry materials are more prone to wind-driven erosion and landform development. And the several Julian landforms includes sand dunes. It is formed in deserts and coastal areas due to wind-driven sand accumulation. Various types of sand dunes includes Barchan dunes, parabolic dunes, transverse dunes, and longitudinal dunes. Next is loess deposits. It is composed of fine wind-blown particles accumulate in regions with significant sources of fine-grained materials and flat exposed landscapes. Next is the yardangs. Streamlined elongated ridges formed by wind erosion occur in regions with parallel wind patterns and soft rock layers. Next is the desert pavements, are surfaces covered with coarser fragments resulting from wind erosion removing finer particles. And lastly is the ventifacts, rocks shaped and polished by wind abrasion, indicating past wind patterns, are known as ventifacts. Now let's proceed to our knowledge check. So in conclusion, wind as a gradational agent is a fundamental force in shaping the Earth's surface. Through erosion, transportation, and deposition, wind contributes to the formation of various Julian landforms. While not as effective as other agents like water, wind still contributes to the landform development. It forms unique features like sand dunes, loess deposits, yardangs, and ventifacts. Specific example like the Namib Desert and Great Sand Dunes National Park showcase wind impact on the land. Overall, wind is a dynamic continuous process that contributes to the ongoing evolution and formation of diverse landforms on our planet. Understanding its role as a gradational agent is essential in comprehending the complex interactions shaping the Earth's surface.